Today we're going to move on to limits. Now you might think, hang on, I know limits, but for functions of two variables it's much more difficult. And I'll show you why. It's a natural extension, but it's much more difficult. This is what we're going to look at, limits and continuity. Now you may have some rough idea of what continuity for functions of two variables means. I guess if you think of the graph of the function, it's like a surface, and that function will be continuous if there's no holes or sudden jumps in the surface. Okay? All right, so let's have a look at some ideas involving limits. Now, yes, you've already seen limits at school, but for functions of two variables, you've got more general domains. You've got a two-dimensional domain. Okay, so just to sort of put this into context, okay, think of this sort of, these two sets lying in the xy plane, and then you've got a surface above or below or maybe interacting with that two-dimensional set. So think of these two pictures as two possible domains for a function, and it's lying in the xy plane. Now, let's just suppose that x0, y0 is a point somewhere in the domain of a function. Now, limits, remember, are all about what happens, does the function have any particular behaviour as we approach some point in the domain? Now, with a two-dimensional region, you can approach a point from many different directions. For example, let's just take this one here. I can approach this point, say it's, I don't know, 1, 2 or 2, 2 or something. I can approach it from this direction, from this direction, from this direction, from this direction, like that. So there's lots of different ways that you can approach a point in the domain of a function of two variables. Now in first year, you learn about left-hand limits and right-hand limits. And you learnt that the limit exists if and only if both of those limits exist and are equal. This is different. There's no left-hand or right-hand limits in this two-dimensional setting. Okay, if you're at the point here, well, how do I approach that from the left? Well, you could argue that way. And that way, well, it's not wide enough. It's not a wide enough idea for functions of two variables. Now, at this point here, think of this as the boundary. This edge is the boundary of the domain. If I've got a point on the boundary, then I can only approach that sort of, along these sort of directions. I can't come from out here because I can only approach points through a path in the domain of the function. Right, so the important thing is, when we look at functions of two variables, you can approach a point from many different directions. Not just from a left-hand and a right-hand sort of side. So that's what we're going to talk about today. We're going to talk about the formal definition of a limit in this context and also continuity. Okay. So here's the formal definition of a limit. Now we know that we don't use this definition all the time to calculate limits, right? In our day-to-day mathematics, we don't use that. We don't always use epsilons and deltas and things like this. But it's good to know about the proof when you want to prove something. So we're going to do a little bit with this epsilon and delta definition, and of course we're going to look at the computation just without this. So we're covering all our bases. So let's try to break it down. What does this definition mean? Students generally get confused with this definition. So what does it mean? Well, suppose L is a real number, okay? Like 2 minus 1, 0. We say a function of two variables approaches the limit L as its variables approach some point in the domain, and write down this, if for every positive number, let's say call it epsilon, we can choose or construct a corresponding number delta, which is also positive, such that this is less than our epsilon whenever this is less than delta. Now, what does that mean? Well, let's try to break it down a little bit and understand it. What does this set represent? Anyone know? In two-dimensional space, what is that set on the right-hand side? So it's like a circle, a disk, right? So if I go back to my previous picture, think of this as representing all the points in a disk with centre x0, y0 and radius delta. Okay, because we're working in two dimensions, how do you measure distance? Well, you need to sort of, extend your, it's no good using absolute values, we need to extend the idea of distance, I guess, in two dimensions. Now, so this is just a disk with centre x0, y0 and radius delta. Okay, so what does it mean? Okay, you give me an epsilon, just choose a number, some positive number, and I can always construct a disk by choosing some disk with radius delta. I can choose the delta or construct it, such that for all points in that disk, I can make the distance between the function and the limit less than the epsilon that you've given me. Now that's got to work for every epsilon, every positive value of epsilon. You can also think of this, I guess, in simplest terms, in distance. Okay, this is what this paragraph's about. Roughly speaking, this definition says that the distance between the function and its limit becomes as small as we want, arbitrarily small, when the distance between the points in its domain and the limit point is sufficiently small. Okay. All right. So let's actually do. So can I just have a show of hands? Who's seen something like that from last year? Anyone? Okay, a few people. It is quite a shock to the system, but today's lecture is going to hopefully explain this. Now we know, I'll come back to the epsilon-delta type stuff in a minute, but let's just look at some practical limit laws. And they're exactly what you would expect. You guys know about limits, and you know how to evaluate them for functions of one variable and vector, including vector-valued functions. So you've got the normal limit laws that you would expect. Okay, in all these cases, we are assuming that the limit of this function is some finite value, and I guess it exists and it's some finite value, and the same with the g. Okay. Now, when we, if you calculate the limit and you get, the function goes off to infinity, we technically would say that that limit doesn't exist because it's not a real number. Infinity is not a real number. Okay. All right, so there's some good practical properties, but let's actually do a simple problem and see how we use this and how we can take limits. All right, here's a function of two variables. Calculate the limit as x, y approach 1, 2. Okay, so now, let's just look at the limit of the top. Okay, I've got a polynomial on the top and a polynomial on the bottom. Any ideas on how we might evaluate that limit? I'm not talking about epsilons and deltas here, just day-to-day calculations. Yeah, just sub in the values for this one. This one's quite easy because essentially it's this rule down here. If the limit of the top is L and the limit of the bottom is M, then I can just take the limit of the top, take the limit of the bottom, and I'll get the following. Okay, so the limit of the top is going to be something like 1 squared plus 2 squared plus 1 over 1 plus 2. So I'm going to get 6 on 3. Oh, I'm looking everywhere but the spot I should be. Okay, apologies. I do know how to divide. That was an easy question, assuming you can divide. Because the limit of the top was some finite number, the limit of the bottom was some finite number, you can just, and non-zero, and you can just sort it out. What about something a little bit more involved? So I'm just going to just construct another example here. Oh yeah. Okay, maybe it looks familiar. Any ideas on how we might calculate the limit here? Factorise the numerator, right? I mean, if we just plugged in numbers here, we'd get something like 0 over 0, indeterminate form, so we can't really do much with that unless we dig a little deeper. Okay, so I'm just going to factorise the top. Cancel. And so just taking the limit, I'll get that. Okay, so nothing too magical yet. Can anybody, there's one sort of path or one way that I can't evaluate that limit along. Anybody know what line it is? That bottom one that I've just done. Yeah, who said that? Yes. Remember, whenever we calculate limits, we're assuming that we're approaching the point in question, in this case 1, 1, through paths or lines that are all in the domain of the function. So, of course, here, the line y equals x isn't in the domain of this function, so we can't approach 1, 1 along that line. So that's sort of implicitly understood. Okay, well, there's a couple of easy examples. Let's move on to something a little bit more challenging. Here I've defined a function. We're asked to formally prove that f of x, y approaches 3 as x, y approaches the origin. Okay, so now we're actually going back to the epsilon-delta type definition. Okay, so for this example, the limit, big L is just 3. And our point of interest is just the origin. So let me explain this as best I can, because there's a definite process with a lot of these problems. You want to construct a delta. such that the definition on the previous page works for that f, that L, and that x0, y0. So let me show you what I mean. Now, usually the delta depends on whatever the epsilon is, right? So by the definition, I mean the definition on the previous page. So how do I do that? Well, what I like to do is just play with the bottom line. Now that might involve some sort of inequality, something like that. So let me show you what I mean for this example. So here the f is this, the L's that. So what I want to do is simplify and maybe form some sort of inequality. So of course I can cancel off the 3's, that's no worries. Now x squared plus y squared is always non-negative, so I can get rid of the absolute value signs as well. Now, how can I make that bottom line less than any positive number, epsilon? Well, I want to restrict root x squared plus y squared in some way. Let me show you how I do that. This will be less than epsilon when what should the bottom right-hand corner be? When is x squared plus y squared strictly less than epsilon? Well, it's when root, x squared plus, it should be a plus there, plus y squared is less than, what? Well, all I need to do is just take the square root. If that's true, then that's definitely true. Right? So what I've done there is I've constructed my delta. I've constructed my delta, and I'm going to say for every epsilon, I'm going to choose delta to be root epsilon. So you give me epsilon, I can give you delta. I'm constructing delta. Now that's a pretty common way of working. That's the way I like to work these problems. Questions? You look worried. Everything all right?
Yeah.
Yeah, you cool? You're not worried though, are you?
No.
You can do it. You can do it. You can do it. No, that's all right. That's all right. That's okay. I'm not, it's okay. Questions? But essentially what you want to do, the method, is to simplify this till you get something like this. We didn't quite get the root here, but it's not a big problem. I can deal with that. All right, something a little harder. If our function f of x, y is defined in this way, then formally prove f approaches 0. Now, firstly, and I probably should have done this with the previous one, are we actually convinced that this function does go to 0 as x and y go to 0? Yeah, it seems reasonable. Just take the limit at the top, you get 0, the limit at the bottom's 1. So we would assume that the limit's correct. Now let me show you how you would do this. And it's very similar to the previous problem, just with a couple of inequalities. So here, this is our L, this is our x naught, y naught. Now, let's play with this and see how we go. Well, the 0 can disappear. X to the 4th plus 1 down the bottom's always positive. But what am I going to do with the top? Now, let me introduce you to a really, I guess, something that you can use. Let's look at that absolute value of y. Okay? The first thing is that this is just less than or equal to this. Now, this relies on the fact that this is true. So if you wanted to write an extra line here, you can write it like that. Pretty sneaky. Now, is there any way I can get rid of the x to the 4th plus 1 somehow? Maybe using some sort of inequality. What's the minimum value of x to the 4th plus 1? 1, right. So I can go down like this and say, well, that is less than, oh my God. Now we're at a good spot. For any given epsilon, what do I have to construct delta to be, or what do I choose it to be, such that I have the inequality in the middle of the screen? What should I choose delta to be in this case? Oh, maybe if I cover that up, it's a bit easier. Root x squared plus y squared is less than epsilon when root x squared plus y squared is less than, oh, epsilon, yes. Right. So it's not, that's what I choose. I'm going to choose my delta just to be epsilon, okay? Now, you might think that's a bit confusing, but remember, you're constructing delta and it's going to depend on epsilon. So thus, we've proved that the limit is 0. Yes?
In the last example, when you got to this position,
yep.
you played with root epsilon.
Yep.
Why not?
Okay, that's an excellent question. I'm really glad you asked that one, because there's no square root sign here. Okay? Yeah, that's a really good question. Yes. Oh, okay. So I've got a less than or equals to, right? Square root is an increasing function. So, if let's say x is say 1, is y squared less than or equal to y squared plus 1? Yes. Is y squared less than or equal to... But basically I'm adding... So forget the square root signs. Right? Do you agree that y squared is less than or equal to x squared plus y squared? So there you have it. You know what I mean? If you take the square root of a larger number, then you're going to get a larger number, right? Okay, so that's kind of delicate from there to there, because what you want to do is come up with something like this, something involving x squared plus y squared. So you have to fiddle around with it. Now you might be sitting there going, "Come on, Chris, that's just magic. I can't do that." You can do it. You can do it. Okay. You need to have the inner monologue going and thinking, "Okay, I've got this problem in front of me. How do I solve it?" Well, you want to be looking for a special form. Something that involves x squared plus y squared when you're approaching 0, right? And where does that come from? This guy here. So play with that until you get something like that. Luckily for us, the x naughts and y naughts are 0 in these examples. So the algebra is not. It could be worse. Any other questions? So I guess if you want to write down something else, you would have x squared is less than or equal to that. Any other questions? Okay. Now, like I said before, you don't always need to use epsilons and deltas. And in particular, a very, very powerful technique is the following test that we're going to learn. This should almost be, well, not necessarily, but this is very powerful because it's simple and it's kind of a generalization. You know, in first year, you might say, show that the following limit doesn't exist, say x approaches 2 or something. Well, you look at the left-hand limit as x approaches 2 from the left, you look at the limit as x approaches 2 from the right, and you show they're not equal. Okay? Or they don't exist. This is a generalization of that sort of left and right-hand limit test. So let's have a look at it. If a function f has different limits along 2 different paths or 2 different lines, as x and y approach our point of interest, then the limit does not exist. So what does that tell you? For a limit to exist, it doesn't matter what path you go down to the point that you're approaching, the limit has to be the same along every path. So if you can find one path where the limit's one value and another path where the limit's another value, you know the total limit can't exist. Okay, so let's just put this into some context. Okay, show that this particular function has no limit as we approach the origin. So what you've got to do is just pick 2 paths or 2 lines and show that the limits along those lines are not equal. So I'm just going to choose the line y equals x and the line y equals minus x, I think. Now I'm going to write up here because I'm going to show you a more general method to do. So the limit, so if y equals x, I can replace y in here with just x. And it's the same. Okay, so let's go in here and, I guess I don't need to keep repeating this, but let's replace y with x, so we get 3x to the 4th over here. And down the bottom, I'm going to get x to the 4th plus x to the 4th, which is 2x to the 4th. So I can cancel those off. So my limit is going to be 3 on 2. Now let's approach, so to give you a picture, what's happening here is that we are approaching 0 along this line here. All right, what about another line? Let's just choose another simple line, say y equals minus x. Well, you do the same thing, and you're going to get the cancellation, but you're going to get a minus up the top, okay? Because you've got you'll replace y with minus x. Compare our two answers, they're not equal. So by the two-path test, right, the limit can't exist. You with me? You're feeling it, man. I can see a lot of you smiling. It's good. But let me show you something better. Let me show you a even more powerful test than that. Because you might go, come on, Chris, how do I know you choose y equals x and y equals minus x? Well, let me show you a powerful test. In general, just consider the line y equals alpha x. So that covers the two previous cases and many more. If you approach 0 along the line, y equals alpha x, and you get alphas in your final answer, you know that, if you go along different lines, you're going to get different limits. So here alpha is just a constant. So f of x comma alpha x. So up here, we're going to get something like 3 alpha x to the 4th over, now that's going to become alpha to the 4th x to the 4th. So I can cancel off the x to the 4ths. And in particular, it's a function of alpha. So if I change my line, y equals 2x, y equals 3x, my limit's going to change. So that's really important. All you have to do is show that the limit depends on alpha. Show that it cannot, and so it cannot exist. Now, you may get problems where even if you put in y equals alpha x, it still doesn't give you what you want. So what's another simple path, say, when you're approaching the origin? A parabola. Y equals alpha x squared. So another good curve. Y equals alpha x squared. So this is not connected now. Say for f of x, y, 2x to the 4th over x to the 4th plus y squared, where we're approaching the origin. So another good curve is that one. So straight lines will work for certain examples, but you're going to have to get a little bit more exotic for other ones. Okay, essentially it's all about cancelling off and seeing if an alpha still remains. So the two-path test is very powerful. Very powerful. Okay, so you should try this one. show that the limit of this function as we approach the origin doesn't exist. All right, now we can't talk about limits without talking about continuity. Just to refresh everyone's memory, continuity is really important because if we know a function's continuous, we can do things with it. If we know the function's differentiable, then we can do even more things with it. So let's have a look at the definition of continuity. So suppose x naught, y naught's a point in the domain. We say the function is continuous at the point if, well, the point's in the domain of f. The limit as we approach the point exists. And in particular, the limit is equal to the value of the function at that point. So it's a special limit. The limit is the value of the function. So big L would be f of x naught comma y naught. And again, just sort of using slang, we sometimes say just a function is continuous if it's continuous everywhere in its domain. Now, let's look at an example. Here's a function here. Show that f is continuous at 0, 0. Well, you might be thinking, well, what's this? I guess this question has two parts to it. I didn't really say prove here. I probably should have said prove. But we'll show it, and then we'll prove it. And to prove it, we're going to use a special inequality called Young's inequality. Now, Young's inequality is really powerful. You need to have it in your kit bag for when you're tackling these kinds of problems. So, one, let's just show that the function is continuous. So, can anybody explain to me, if we want to show the function is continuous, what do we actually want to do? What do we want to produce? What's the method? What's the inner monologue? What's that? Say again? Can you just... Yes. Right. Thank you. Didn't you hear me before when I was talking about phones, right? So just... Anyway, show that the limit is just the value of the function, which is just 0, right? So essentially, we just want to show that the value of the function is 0. Sorry, the limit of the function is 0. So what's the value of the function at 0? Is just 0. Okay, so we don't need to really prove anything, so let's just compute it. The limit of 2xy as we approach 0 is 0. The limit of the bottom, 2 plus sine x, is going to be 0. So all right, so just on a practical level, that's how we do it. Now, if I wanted to prove it, how would I do that? Well, this is where you use the hint, so-called Young's inequality. So let me show you. This is really a real powerful tool. So what we actually want to do now is prove that this limit really is 0. The limit of this function... Oh, sorry, hang on. I'll just put... So this is just down here. Okay, sort of abuse the notation there. Okay, how do we do that? Well, consider. So my limit is 0, my function's here. So let's just look at the difference between the function and its limit. Now, that's going to disappear. I can use this inequality up here now on the top. So that's disappeared. I'm going to get x squared plus y squared on 2 plus sine x. Okay, so from here to here, that disappeared, and I've used Young's inequality. Now, anybody suggest what else I can do? I'm still a bit confused. I need to get that, work on that bottom, the denominator, right? Yes? Oh, I would, yeah, I would. I mean, I'm saying it to you now. Well, I can write it in if you want. I would recommend it. Yeah. So let me write it down. I would totally recommend it. Now, what about the bottom? Well, sine x is between -1 and 1. So 2 plus sine x, that's going to be between 1 and 3, right? So what I can do is again use the little inequality. So what if I want to make that less than a given epsilon? All I need to do is choose delta to be that. So Young's inequality, really powerful, really important. Okay, see if you can justify how I've gone from here to here. It just relies on this. Okay, now, good example, show that this function's not continuous at 0, 0. So the function's defined kind of in a split fashion. How would you show that this function's not continuous? Well, when we want to show a limit, I guess all we really want to do here is show that the limit of the function's not 0. So you've got a choice here. You can either try to calculate the limit and show that it's not 0, but maybe the limit doesn't exist. Your first port of call should be trying to show that the limit doesn't exist, because it's the easiest test. Just use the two-path test. So I'm going to show in this case, for this example, that the limit doesn't actually even exist. So of course it can't equal 0. So the two-path test. So I'm going to actually approach the origin along, the lines y equals alpha x. All right, so basically we're going to take alpha x and replace y in here. sorry. Yep. And now you can see I can cancel off those x squareds. So I'm going to get something like 1 plus alpha squared, which is dependent on alpha. So if I go along different lines, as long as they're in the domain, I'm going to get different values for my limit. So the limit can't exist. Like I said before, if alpha x doesn't work for you, so you might put in alpha x and you'll get x's and alphas. You can't do anything with that. Try alpha x squared. That usually sorts things out. Now, the last slide is about a neat little trick. This is like a last resort. If you try to calculate these limits and nothing works, you're trying direct methods, you're trying the two-path test, you're trying all sorts of stuff, sometimes polar coordinates can come and help you out. So as a last resort, switch to polars, and then if the limit exists, then you can just consider this limit rather than this one. And of course here we're approaching 0, 0, right, the origin. So for this one, we want to show that f approaches 0 as x and y approach 0. So let's actually replace x with r cos theta and y with r sine theta. So up top we're going to get this, and down the bottom we're going to get this. Now cos squared plus sine squared equals 1. I can cancel off the an r squared. So I'm going to get something like this. Now, as r goes to 0, what happens to this? Well, cos is just between -1 and 1. So if we send r to 0, the cos cubed theta isn't going to come into play at all because it just goes between -1 and 1, so it doesn't go off to infinity or something. All right, guys, I'll see you all on Thursday.